here's the second page of assignment 146. You can see this is high level. These are at least AP chemistry, maybe beyond. What we're looking at here is the idea that instead of counting molecules, you usually, or percentages, you have things called rate constants. So you've seen equilibrium constants represented by a capital K. These are rate constants represented by a lowercase k. But I'm hoping this makes sense to you. It can be summarized this way, that there'll be a K1 that turns the weak acid into its dissociated ions. There'll be a K2 that brings them back to the weak acid state. And the ratio of these determines the equilibrium. So here is a reasonable number for a rate constant for the dissociation of a weak acid. You see now it's not a percentage, it's 6 times 10 to the minus 6. But the rate of dissociation will be that K value times the molarity, the concentration of the weak acid. Alright, so here we go. If the molarity is 0.5 molar, then this is actually quite easy. Rate equals K1 times the molarity of HCOOH, which in this case is 6 times 10 to the minus 6 is K1, and 0.50 molar is the concentration, and so the rate is 3 times 10 to the minus 6 moles per second. Okay, so now, same idea as before, but now we're talking about moles per second, which should look to you more realistic for a beaker that has millions and millions of molecules. That's what B is about, saying how many actual molecules are we talking. Avogadro's number, you should remember, is the 600 million billion, which is 6 times 10 to the 23rd molecules per mole. And here we have 3 times 10 to the 6. Sorry, 3 times 10 to the minus 6 moles. So that's going to be 18 times 10 to the 17th power, which is 1.8 times 10 to the 18th molecules per second. Okay, so now what this is saying is that in a beaker that has half molar formic acid, a huge number of molecules are dissociating each second. But if it is at equilibrium, that's balanced by an equal number coming back. And that's what this table is about here in C. It's saying K2 is 3 times 10 to the minus 2, which is actually a much bigger rate constant than K1. K2 is much bigger than K1, and that in Ms. Holtz's demonstration, this is the big beaker, right? This is the big beaker that made it so that it was relatively easy to go back to the associated state. So beaker size can be related directly to these rate constants. This right here, K1, is relatively small, and therefore a relatively small beaker in the model. Alright, so I'm hoping this first one makes sense to you. If we have K2 is 3 times 10 to the minus 2, and we're getting a rate, it's actually, as can be seen here, K2 times H plus times HCOO minus molarities. So here they're both 1 times 10 minus 2, so I can mathematically say 1 times 10 to the minus 2 squared. And that comes out to be 3 times 10 to the minus 6 moles per second, which is equilibrium. It balances the rate of dissociation. I should label this. Reassociation is equal. We have equilibrium. This is just a mathematical exercise. So if you do line 2 and you just say rate constant is always the same, that's what makes it a constant, 3.0 3 times 10 to the minus 2, and now they're not the same, so it's 2 times 10 to the minus 3 and 5 times 10 to the minus 2. But if you multiply all those out, you should get the same number, 3 times 10 to the minus 6 moles per second, which means that once again, this is an equilibrium state. Nothing is equal anymore, but it's still an equilibrium state because the arrows are equal. Arrow, arrow. Alright, with that in mind, I'm hoping you have already calculated these. If you haven't, you can try to match my answers. This is not an equilibrium because it does not equal the rate of dissociation. And the last one is also not in equilibrium. And that leads to D here. If you analyze this well, you should say association rate is greater than the dissociation rate. And therefore, that's not equilibrium. It has to shift to get there. Here, the dissociation rate is greater than the association rate. And that's, again, not equilibrium. It'll have to shift to get there. Here on the bottom of the page, I'm using my same arrow technology I showed you before. We have numbers for the association and dissociation rate in line 3 and in line 4, so I'm doing one at a time. Line 3, the dissociation rate is 3 times 10 to the minus 6 moles per second, and the association rate is 4.8 times 10 to the minus 5, which is a bigger value, and that's why I've drawn a bigger arrow going to the left. So this one must shift to the left. The arrows tell you that, the numbers tell you that, so that more formic acid will form, less ions will exist. That's how it will reach equilibrium. For number 4, it's exactly the opposite. The arrow pointing to the right is the same as it ever was. Same as it ever was. 3 times 10 to the minus 6 going to the right. Arrow going to the left, however, is puny. Only 6 times 10 to the minus 10 is coming back. And therefore, this one must shift right to the right. That produces more ions to reach equilibrium. Alright, the last one is easy math if you just start with this. K1 times HCOOH equals K2 times the dissociated ion molarities. You should easily be able to use algebra to turn that into that.